Okay, welcome to my presentation on human immunity. So in this presentation, we've been looking at a few things, but some of them are the non-specific lines of defense in our body against foreign bodies and pathogens. Some examples of specific immunities, so once we get past the non-specific, and then the biology of vaccinations and some other stuff about that. So non-specific lines of defense, what are they? Well, those are the lines of defense our body has against external threats, which are present from birth. They do not distinguish between different pathogens, and they have the same response to all of them. And they are generally very effective against a wide variety of pathogens and foreign bodies. Now, when I say pathogens, what that could mean is stuff like fungi, bacteria, viruses, or even parasites. Okay, so some examples of our first line of defense is our skin and our mucous membrane. So our skin is a mechanical and physical barrier against potential infection or entry from pathogens. It's our waterproof coating that protects all our vital system and organs. It's the largest organ in our body, and it is constantly replacing itself on a 28-day cycle. As old cells die off and fall off at the top, new cells are multiplying and producing at the bottom. So here we have this general structure. You have the epidermis at the top, the dermis in the center, and the subcutaneous fat at the bottom. Within that we have the nerves, blood vessels, sweat glands, and our melanin. Our melanin's an important one to look at because this is the cells that are actually protecting us from UV radiation, which obviously has the potential to cause a lot of harm to our cells, obviously potentially to cancer. Okay, the second is our mucous membrane. This is the other first line of defense. Now, where we don't normally have skin, we have these. This is mucous membrane. It's a membrane lining, body cavities and canals that lead to the outside, chiefly the respiratory, digestive, and urogenital tracts. So these are obviously the important thing about these is that we want to allow some stuff in and out, but obviously not everything. We want air and oxygen to get through our respiratory tract to our lungs, but we don't want to be breathing in all the fungi, all the bacteria, and we don't want to let that into our system. So these are obviously very important for that, to be able to regulate that. And how one of them does that, our eyes, for example, is they produce in our tears an alkali, which is very effective at killing bacteria. So we move on to our second lines of defense. And inflammation is a great example of that. So a quick definition of, inflammation, there's a tissue injury caused by physical or chemical agent or pathogenic microorganisms that's causing the inflammation. And what we're going to see from that is the capillaries are going to start widening. You're going to see an increased blood flow to the site, increased capillary permeability. You're going to see the space is going to be opening, which is going to allow the release of fluid. We're going to see an attraction of white blood cells, and which is going to allow those to migrate to the source of injury. And the systemic response of fever and proliferation of white blood cells. Now, all of this will lead to symptoms in the area of heat, redness, tenderness, swelling, and pain. I'm sure we've all experienced that if we've had a cut or infection in a certain area on our skin, perhaps. Now, another second line of defense is fever. Now, that is our body's attempt to raise our core body temperature to try and slow down the production or reproduction of bacteria. Okay, so this is another second line of defense. Still in the non-specific, so these are attacking anything generally. Those white blood cells we saw could be macrophages. Now, these are a phagocytic tissue cell of the immune system that may be fixed or freely mobile, is derived from a monocyte, and it functions in the destruction of foreign antigens such as bacteria and viruses and serves as an antigen-presenting cell. So basically, these are a type of our white blood cells, specific type, that they are some of our frontline workers. They are consuming and enveloping the antigens and pathogens and destroying those. Now we get on to acquired immunity. So we're starting to look at our third line of defense. Now this is when we start getting specific. Now these are different to non-specific. These are not present from birth. So these are gained during life, learned or introduced into the system in whatever ways. Now, for the body to detect and therefore fight an invasion or a foreign body, whatever it is, it needs to detect it. And what it's detecting is the antigen. Now, if we look at these diagrams of a bacterium and a virus, you see these things on the outside. These are the antigens. These receptors are what our body's detecting. And our sensitivity to the specific antigens is going to be how effective our body is at targeting or even noticing it to therefore start attacking it. Now, artificially acquired immunity can be passive or active. We're going to look at that a little bit more in a minute. Okay, so immune system cells. So these are our white blood cells, basically. These are all leukocytes, and there's lots of different types. Ranging from the most common, the neutrophils, which range from 2,000 to 7,500 cells per millimeter cube of blood, down to the least common basophils and eosinophils. But the neutrophils, lymphocytes, which we just discussed, and that we're going to discuss in a moment, and the monocytes, which are macrophages. These are the workhorses. These are the ones that are going to be, just destroying most of the stuff. Our lymphocytes are our T cells and our B cells. And now these two are a lot more rare, the basophils and eosinophils, and they're a lot more specific and niche in their functions. The eosinophils, these are the ones that are targeting parasites and worms generally, and the basophils are ones that are able to release chemicals to mediate the inflammation and allergic responses of our body. Okay, lymphocytes. So, like we said, these are the T cells and the B cells. Now, looking at what a B cell is and what it can do, a B cell is triggered when it encounters a matching antigen. The B cell will then engulf the antigen and digest it. It then displays antigen fragments bound to its unique MHC molecules. Now, our cells, instead of antigens, we have these MHC molecules. This is our friendly antigen almost. This combination of antigen and MHC attracts the help of mature matching T cells. So these two lymphocytes work together. The cytokines secreted by the T cell help the B cell to multiply and mature into antibody-producing plasma cells. Now that's the important part. Now the B cell has then identified the antigen, digested it. With the help of the T cell, it is now producing these antibodies or immunoglobulins, whatever we want to call it. Now to define the immunoglobulins, the glycoproteins produced by B cells called antibodies or immunoglobulins recognize and bind free antigens and are responsible for immunity. So that's what these antibodies are doing. That these are the ones that are binding to the foreign bodies, their antigens, and allowing us to then attack it. And this is a little diagram of an immunoglobulin, and you can see the two areas at the top. These are the antigen binding sites. So these will be a unique shape and structure depending on the antigen it can specifically target. So our second type of lymphocyte is our T cell. You have three types of T cells. You have the cytotoxic, the helper, and the suppressor. Now the helper is the most common. That's the one we just saw, the one that's aiding the B cell. The cytotoxic generally helps defend against viruses, and the suppressor is one that can suppress the other two, the amounts of them, to help regulate the immune system. And generally you can compare the two. B cells are attacking invaders outside the cells, and T cells are attacking infected cells. So the general functions: they can signal for growth and the activation of B cells, they can activate cells that can consume foreign bodies, they can encourage the growth in cells to produce other T cells, macrophages, and eosinophils, and they can stimulate cytotoxic T cells. Okay, self-recognition. So obviously, when our cells detect something is a foreign body, we detect the antigen and our body starts attacking it. However, why isn't our body attacking our own cells? Because we have these self markers. Our body is able to distinguish between self and non-self. Now, the problem with this is that when you look at things like organ transplants, that if the organ that's been transplanted isn't matched very closely to our MHC labels, and our body is recognizing them as antigens and non-self, then our body's going to start attacking that. And that's when we refer to it as an organ being rejected when it's been transplanted. That's why it's essential for it to be as closely related as possible. As we briefly discussed, the sensitivity to antigens. The more sensitive our body is to a certain type of antigen, the more aggressive, the more fast a reaction is going to be towards that. And the less sensitive or not sensitive at all, our body probably won't react to it. So again, if the organ transplanted, if we're just a lot less sensitive to that type of antigen, then that might be a bit more successful. Okay, so immune system disorders, going on from that. An autoimmune disease is an illness that occurs when the body tissues are attacked by its own immune system. So yeah, this is our body not recognizing it itself. The immune system is kicking in, and we're going through those stages against our own body, something obviously we don't want. Now, some symptoms of autoimmune disorders are redness, heat, pain, and swelling. Pretty obvious. This is obviously the inflammatory response. Now, an example of that is rheumatoid arthritis. So Over here is the stages of rheumatoid arthritis. Right from the left, we've got the healthy joints. This is obviously before it's starting to set in. You've got your bones, your cartilage, and the fluid. Now, as it starts to swell, you're getting that inflammation, the heat. It's going to start eroding the bones and the cartilage, and eventually you're going to get to the point where the bones can just fuse. And now this can happen in any joints in our body, and this is just our body attacking itself. It can be our fingers, our wrists, our knees, and it obviously can be extremely painful for whoever's going through it. Now, our second type of immune disorder we're going to look at is Crohn's disease. Now, Crohn's disease is an immune-mediated disease that can affect any part of the digestive tract, from the mouth to the anus. Again, this is our body. Our body is going through the immune response. We're getting inflammation, all through our digestive tract, or potentially all through our digestive tract, which can cause ulcers. Now, a lot of what's actually causing Crohn's disease is largely unknown, but it's assumed to be that the body is attacking the good bacteria of the stomach and the digestive tract, which is allowing for this extra damage. And whilst some causes of autoimmune disorders, what's starting all this off in the first place? It could just be our encounters with a bacteria or a virus that can then set off a chain of reaction. Some drugs, chemical irritants, environmental irritants. A lot of things can set our body off to change how it's reacting, and the immune system start attacking itself. Okay, acquired immunity. So we have active immunity and passive immunity. Now, active immunity is when our body is doing it itself. Our body is fighting the virus, it is identifying it, it is learning it, and then it is combating it. So we've got natural active immunity. This is probably the most common. So when our body encounters, say, a cold, the B cells are going, the B cells are identifying it, the T cells are helping that, and then we're producing antibodies, and that's how we build a natural active immunity to whatever that was, or that specific cold strain. Now, an artificially induced active immunity is our body isn't fighting the normal healthy version of that virus or pathogen. We are perhaps giving a vaccination, which is a damaged or a dead fragment of that pathogen, meaning our body has a much greater chance of the fight. We can quickly identify it without having all the symptoms. But we'll look more into vaccinations in a moment. And so passive immunity is where our body's not doing that. Our body's not going through the processes of our B cells getting involved and our T cells. And our natural passive immunity, that can be via breastfeeding, where the mother is passing over those immunoglobulins straight through the breast milk, and those are then fighting the pathogens inside our body. Or artificially induced passive immunity, where they're actually just being injected straight into you. And again, our body isn't having to learn, it isn't using our cells to do that. And it's not just a case of laziness. Obviously, if you perhaps cannot produce the immunoglobulins, then this is obviously a very useful thing. And for babies who don't have the same ability, again, the natural passive immunity for breastfeeding, very, very important. For example, if you get AIDS, this would be quite important, because AIDS is what's destroying your T cell count, and therefore your immune system can't function as much as it normally could. Okay, so vaccinations. Now, a vaccination, as we quickly said, is a harmless or dead fraction of the pathogen entering the system. The body is then able to identify it, and then once it has, you can build up this immunological memory. Now, this can be defined as the capacity of the body's immune system to remember an encounter with an antigen due to the activation of B cells or T cells having specificity for the antigen, and to react more swiftly to the antigen by means of these activated cells in a later encounter. So yeah, we build up this memory once we've gone through the hard work for the first time, which is the primary response, the first time the pathogen's met. It's going to take time on this time for the B cells to identify it, and our body's going to be suffering from the side effects. We're going to go through all the symptoms, or a lot more than we would on the secondary response at least. But once we have gone through that and our T cells have identified it, we're producing those antibodies, we're going to gain this immunological memory. So when that pathogen enters our body on the second time, we go through the secondary response. It's much faster. Those antibodies are already learned and can be produced straight away, and we're probably not going to feel the side effects as severely as we did the first time. Okay, a quick analysis of a vaccination we've had in history in the UK. So this is for measles. This is looking from 1940 up to 2016. And the measles vaccine was introduced in 1968, so around there. And so if we look at the very beginning of the data, in 1940, the measles cases were just over 400,000 reported, and the deaths at 857. Now, by 1968, this is before the vaccine has come out. Well, and in 1968, that's when the vaccine is being introduced. We're at 230,000 cases and 51 deaths. Now, obviously, the amount of cases has only dropped by roughly half, but the amount of deaths has massively reduced. And obviously, that's not because the vaccine's been introduced, because it's only just happened, but this is more likely to do with a better understanding of how to treat it. We've had those 28 years to be able to identify the disease much more, so on and so on. And obviously just the advancements in medicines that probably happened between 1940, post-war, to 1968. And then after this point in 1968, the deaths will never climb higher than 51. From 1990 to 2000, the deaths were all below 10. 2000 to 2010, the deaths were never above 2, with many years only having 1 or no deaths. And 2010 to 17, it should be 16, the same trend, only 1 or no deaths, of which are acute cases of late in life contraction. And you can really see this trend, obviously at 1968, by this point it's gone down quite a bit, but then it is just spiraling off. And by the time we've gone through a whole generation where probably the vaccination has now reached everyone, this herd immunity has been reached, the deaths have fallen off to none or just anomaly cases. Well, on the subject of herd immunity, this is the idea where, say, if you get a whole community of 100 people vaccinated, where therefore they are now immune to a certain disease or pathogen, if a new person enters that community who is not immune, the disease is going to find it very difficult to get through any of those 100 people to that person. So a herd immunity, we're closing down the avenues of spread of the pathogen being able to spread to any individual who is not immune. Now, herd immunity at the moment in our cultures is at risk, at least in the West, because of the anti-vaxxer revolution or groups. And this is where people have strong fears about the potential side effects of vaccinations, especially potentially leading to autism and a lot of other wild and crazy theories. Obviously, this puts into threat the herd immunity because the herd immunity is essentially important because not everyone can take these vaccinations. So you have the very, very young and the very old and frail who are unable to take them. So they are still vulnerable to these diseases. Now, if we stop vaccinating all the generally healthy people, we're giving so many more avenues of infection to the ones that can't be protected. Now, uptake of vaccines in communities is obviously very important, and to make it as accessible as possible, in the UK we've given over the role generally to pharmacists, so you can go obviously to most high streets, most corners, and you'll find your pharmacy, and in there you'll be able to book and get your vaccinations, which is obviously very, very important, so we can get as close to this point of getting to herd immunity. And with some diseases we've almost eradicated them or have, and that's the point we want to stay at, where the danger of the anti-vaxxer groups is that we can start going backwards, and some diseases that are almost extinct can start coming back into our communities. Okay, in conclusion, so we've looked at non-specific lines of defence in our body, the specific immunity, and the biology of vaccinations. I hope that has involved pants off you. Thanks for watching.